The beginning of the atomic model comes from the Big Bang.
Now we will discuss about the Big Bang Theory first.
What is the Big Bang Theory?
Big Bang Theory explains how the elements originally formed from the formation of the different elements and elements evolved, meaning nuclear fusion, fission, and radioactive decay. And part of its proof is the amount of this hydrogen and helium we have in the universe today,
And there are three stages of Big Bang Theory.
namely singularity, inflation, and heliocentricity.
Singularity, a point in space, are a moment in time where the universe was infinitely flat and dense.
Inflation is a theory of exponential expansion of space in the early universe. The inflationary epoch lasted from 10 to the power of negative 36 seconds.
Nucleosynthesis is the process that creates new atomic nuclei from existing nucleus, primary protons, and neutrons.
Cosmology is a branch of astronomy that involves the origin and evolution of the universe. From the Big Bang to today and into there are three cosmic stages through which a specific groups of elements were formed. First, Big Bang nucleosynthesis formed the light elements, hydrogen, helium, and lithium. Second, stellar formation and evolution form the elements heavier than beryllium and iron. Third, stellar explosion or supernova form the elements heavier than iron.
There are scientists who make experiments and contribute the formation of atomic models that prove on how the elements were continuously evolved and study the elements in the previous table.
A model is a great representation of a system in the real world. Model help us to understand system in the
It is important to realize that a lot of what we know about the structure of atoms has been developed over a long period of time. This is a system how scientific knowledge develops with one person building on these ideas of someone else. We are going to look on how our modern understanding of the atom has evolved over time.
The idea of an atom was invented by the Greek philosophers Democritus and Leucippus in the 5th century of before. The Greek word atomo or atom means indivisible because they believed that atoms could not be broken into a smaller pieces.
Nowadays, we know that atoms are made up of positively charged nuclei in the center surrounded by negatively charged electrons. However, in the past, before the structure of the atom was properly understood, scientists came up with a lot of different models or pictures to describe what atoms were.
Niels Bohr's model. Edison argued under Niels Bohr proposed that the electron and orbit the nucleus certain species orbit at different energy levels around the nucleus.
J.J. Thomson model or Planck-Finding model has positively shocked. He said that atoms were made of even smaller particles than they had previously thought. However, the atomic nucleus had not even discovered yet, and so the Planck-Finding model was put forward in 1904, and even the Planck-Finding model was still no understanding.
Rutherford model. Rutherford carried out some experiments which led to a change in ideas around the atom. His new model describes the atom as a tiny, dense, positively charged core called a nucleus surrounded by lighter, negatively charged electrons. Another way of thinking about his model was that the atom was seen to be like a mini solar system where the electrons orbit the nucleus like planets
orbiting around the Sun. A simplified picture of this shown alongside this model is sometimes known as the planetary model of the atom.
Go.
Dalton's model proposed that all matter is composed of very small things, which he calls atoms. He proposed that all matter is composed of small, invisible, cannot be divided objects. Whereas Dalton proposed his model, electrons and the nucleus were unknown.
Two planetary orbit models. From 19 to 1911, Ernest Rutherford proposed the planetary for nuclear model of the atom. He believed that atoms were composed mostly of empty space with a dense nucleus. His experiments involved shooting alpha particles at gold foil. He concluded that the positive nucleus contains most of the atom's mass. With his orbit model, Niels Bohr refined the idea of the atom as a tiny solar system in 1913. Bohr's model had electrons orbiting the nucleus in shell-like layers.
Electron cloud model. Louis de Broglie and Erwin Schrödinger developed the electron clouds or quantum mechanical model. They based the model on the breakthroughs of the quantum mechanics branch of physics. Instead of electrons in fixed orbit, the cloud model has the orbit defined by probability distribution around the nucleus. Depending on their observation and measurement, the electrons could be in many different places, sometimes simultaneously.
An atom is represented at the most basic level in everything we see around us. In fact, every living organism is composed of atoms. Every non-living thing around, such as tables, chairs, whatever, etc., is made of matter. But the building blocks of matter are atoms. Therefore, living or non-living, everything is composed of atoms. Let us take a look at the structure of atoms.
Each successive model of atomic anatomy and construction was based on the previous one. Philosophers, theorists, physicists, and scientists progressively developed the atomic paradigm over the course of many centuries. Several hypothetical models were proposed, modified of many centuries. Several hypothetical models were proposed, modified, and eventually rejected or accepted. Many scientists and thinkers made discoveries and constructed experiments to arrive at the currently accepted atomic model. The development of mathematics and specialized technology contributed greatly to the contemporary understanding of the nature of atoms.
Plum-pudding model. In 1904, the British physicist J.J. Thomson posited the plum-pudding or resin bomb model of atomism. It was based on knowledge of the recently discovered negatively charged subatomic particles called electrons. Thomson's experiments with cathode-safe tubes prompted him to theorize the existence of tiny particles inside atoms that were fundamental parts of all atoms. His model envisioned the negative electrons or plums suspended inside a positively charged framework or the plum pudding.
Early spherical models. Because atoms are too small to be seen, the first theoretical models were intellectual construction based on the logical methods or inductive and deductive reasoning. So, the classical Greek philosopher Democritus was the first to propose the existence of atoms in 400 before Christ. The reason the matter cannot be divided infinitely and must consist of indivisible round particles called atoms. In 1800, John Dalton arrived at the same view of atomism by using the experimental method to study gases and compounds. This theory was called the solid sphere or billiard ball model.
How do you picture an atom in your mind? Like this, or like this, or maybe one of these? If you understand enough about atoms to visualize any of those things, then you know more about atomic theory than scientists did just 100 years ago. And like way more than they thought they knew 2,500 years ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you'll reach a particle that can't be cut anymore. They gave these particles the name atomos, which means uncuttable or indivisible. So basically they thought that iron was made up of iron particles, and clay was made up of clay particles, and cheese was made up of cheese particles. And they attributed properties of each substance to the forms of the atoms. So they thought that iron atoms were hard and stuck together with hooks. Clay atoms were softer and attached by ball and socket joints that made them flexible, and cheese atoms were squishy and delicious. Now this makes a certain amount of sense if you don't happen to have access to electron microscopes or cathode ray tubes or the work of generations of previous scientists. Because the fact is, atomic theory as we know it today is the product of hundreds, if not thousands, of different insights. Some models, like that of Leucippus, were just blind guesses. As time went on, many more were the result of rigorous experimentation. But, as has been the case in all science, each scientist built on what had been learned before. We've been talking a lot about the fine details of chemistry in recent weeks, and we're gonna keep doing that as we move on to nuclear chemistry, and then to the basics of organic chemistry. But before we do, I wanted to set aside some time to explain how we know what we know about the atom today, and how we know that we're not quite done figuring it out. Now you might think that once Leucippus and Democritus came up with the general idea of atoms, it'd be pretty easy for someone else to take that little indivisible ball and run with it. But you'd be wrong. The next major developments in atomic theory didn't come along for nearly 2,300 years. I've already told you, for instance, about the French chemist Antoine Lavoisier, who proposed the law of conservation of mass, which states that even if matter changes shape or form, its mass stays the same. And you should remember the English teacher James Dalton, who determined that elements exist as discrete packets of matter. Thanks to these and other great minds by the 1800s, we had a better grip on the general behavior of atoms. The next logical question was, why? Why do they behave the way they do? This led to the investigation of atomic structure. In the 1870s, scientists began probing what stuff was made of using discharge tubes, basically gas-filled tubes with electrodes at each end, which emit light when an electrical current passes through them. It's basically what a neon light is. Because this light was originally produced by a negative electrode, or a cathode, it was called a cathode ray, and it had a negative charge. But in 1886, German physicist Eugen Goldstein found that the tubes also emitted light from the positive electrode, basically a ray heading in the opposite direction, which meant that there must also be a positive charge in matter. Goldstein didn't fully understand what he'd discovered here. I mean, scientists still hadn't figured out what was responsible for the negative charge in the rays either. Then, English physicist J.J. Thomson took the discharge tube research further. By measuring how much heat the cathode rays generated, how much they could be bent by magnets and other things, he was able to estimate the mass of the rays. And the mass was about 1,000 times lighter than hydrogen, the smallest bit of matter known at the time. He concluded that the cathode rays weren't rays or waves at all, but were in fact very light, very small, negatively charged particles. He called them corpuscles. We call them electrons. So even though we didn't understand what shapes they took, we knew that there were both negative and positive components to matter. The next question was, how were they arranged in the atom? Thomson knew that the atom overall had a neutral charge, so he imagined that the negatively charged electrons must be distributed randomly in a positively charged matrix. And the very English Thomson visualized this model as a familiar English dessert: plum pudding, the positive matrix being the cake, and the electrons the random floating bits of fruit within it. Even today, Thomson's model of the atom continues to be called the plum pudding model. And while a single electron's motion is random, the overall distribution of them is not. The next big step was taken by New Zealander Ernest Rutherford in 1909. He designed an experiment using an extremely thin sheet of gold foil and a screen coated with zinc sulfide. He bombarded the foil with alpha particles, which he didn't really know what they were, just that they were produced by the decay of radium, they were positively charged, and they were really, really small. He expected them to just fly right through the foil with no deflection, and many of them did just that. But as it turned out, some of the particles were deflected at large angles, and sometimes almost straight backward. The only explanation for this was that the entire positive charge in an atom, the charge that would repel an alpha particle, must be concentrated in a very small area. An area that he called the nucleus. Because most of the alpha particles passed right through the atoms undeterred, Rutherford concluded that most of the atom is empty space. And he was correct. Rutherford would later discover that if he bombarded nitrogen with alpha particles, it created a bunch of hydrogen ions. Now, he correctly surmised that these tiny positively charged ions were themselves fundamental particles. Protons. Now we're getting close to reality. So these chemists had a fairly good idea of the structure of the atom, they just needed to figure out what exactly the electrons were doing. Enter Niels Bohr. In 1911, the same year the results of Rutherford's gold foil experiment were published, Bohr traveled to England to study with Rutherford. And as a physicist, he was also interested in the mathematical model set forth by German physicists Max Planck and Albert Einstein to explain the behavior of electromagnetic energy. Over time, Bohr came to realize that these mathematical principles could be applied to Rutherford's atomic model. His analysis of the gold foil experiment, calculations based on the proportion of alpha particles that went straight through, those that were slightly deflected, and those that bounced almost completely backward, allowed him to predict the most likely positions of electrons within the atom. Bohr's resulting model, sometimes called the planetary model, is still familiar to most people, probably including you. It represents the electrons in orbits around a small central nucleus. Each orbit can have a specific number of electrons, which correlates to the energy levels and orbitals in the modern model of an atom. And while it's definitely flawed, Bohr's model is very close to reality in some important ways. But like everyone I've mentioned in the past couple of minutes, Bohr was at once fantastically right and way off. The problem was those pesky electrons. It was the German theoretical physicist Werner Heisenberg who got everyone to understand just how huge and mind-blowing this electron problem was. But he was also the one who helped tie the whole mess up into a neat little bundle. Using his wicked math chops, Heisenberg discovered that it is impossible to know with certainty both the momentum of an electron, or any subatomic particle, and its exact position. And the more you know about one of those two variables, the harder it gets to measure the other one. So if you can't measure the position or momentum of an electron, you obviously can't say with certainty that the electrons in an atom are all neatly aligned in circular orbits. So he and a new wave of physicists and chemists proposed a new theory, a quantum theory, which proposes that electrons weren't particles or waves. Instead, they had properties of both and neither. By this thinking, the arrangement of electrons around a nucleus could only be described in terms of probability. In other words, there are certain regions where an electron is much more likely to be found. We call these regions orbitals. You know, the very same orbitals that you and I have been talking about. The ones that go by the names S and P and D and F and that form sigma and pi bonds. Those are the things that Heisenberg's theory predicts, and that's the modern understanding of atoms. Because it's based on probability, quantum-style atoms are often drawn as clouds with the intensity of color representing not individual electrons, but the probability of finding an electron in any particular position. For this reason, the quantum model is often called the cloud model of the atom. And now you know! All the people I've mentioned and many others put their heads together over time to build this current and, I might say, quite elegant understanding of atomic theory. Now, after 2,500 years, even though we can't see them, we can know what they're like and how they work because a long succession of scientists contributed bits and pieces to the whole fantastic picture. But it's also important to recognize that we still may not be quite all the way right. Thomson's contemporaries were sure that the plum pudding model was right, scientists in Bohr's day fully believed that the planetary model was right, and today we're extremely confident that the quantum model is correct. But it may not be all the way correct, and that's where you come in. The only way we can go on being sure is to keep asking questions and conducting experiments, and that's why you're taking chemistry and physics. Pay attention! Thank you for watching this episode of Crash Course Chemistry. If you paid attention, you learned that Leucippus and Democritus originated the idea of atoms nearly 2,500 years ago, but that the real work didn't really begin until both protons and electrons were discovered by experimenting with discharge tubes, and how Ernest Rutherford figured out what and where the nucleus is. You also learned that chemistry can sometimes be done with just math, like how Bohr figured out his model or the way that Heisenberg used math to usher in the quantum theory of the atom. This episode was written by Edie Gonzalez and edited by Blake DiPastino. Our chemistry consultant is Dr. Heiko Langner, and it was filmed, edited, and directed by Nicholas Jenkins. The script supervisor was Catherine Green, Michael Aranda is our sound designer, and Thought Cafe is our graphics team.